In this video, we're going to look at lumped system approximation, and for that, we're going to need these equations. One is the characteristic length, which is the volume over the surface area of the object. We also need the Biot number, which is the heat transfer coefficient, times the characteristic length, which we found up here, divided by the thermal conductivity. So we're going to use those. Let's take a look at this problem. A rod made of chromium is 0.7 centimeters in diameter and 2 centimeters long. The rod is initially at 5 degrees Celsius. Air then flows over the rod at 35 degrees Celsius. The heat transfer coefficient between the rod and the air is 30 watts per meter squared K. What is the temperature of the rod after 50 seconds? So let's take a look at the solution. We're going to have a rod that's 0.7 centimeters in diameter and the length is 2 centimeters. And so we're going to need to calculate the characteristic length, and that's going to be the volume divided by the surface area. Of course, the volume is going to be pi r squared times the length. And the surface area, we're going to need this surface area here. That's going to be 2 pi r, which is the circumference, times the length. Again, I'll call that L, plus the two ends, and the area of those, there'll be two of those. That'll be pi r squared times 2, like that. Now we can reduce this, and we could factor out 2 pi and an r in the denominator. And that's going to leave us with an L plus an r like that. And then in the numerator, we still have the pi r squared L, and we can cancel out a pi, and we can cancel out one of the r's in the numerator, one in the denominator. So we're going to have RL over 2L plus r like that. So next, let's substitute values into our equation. And again, remember that our diameter was 0.7 centimeters. Let's convert that to meters. Length is 2 centimeters. Let's convert that to meters. Remember, divide each of these by 100 to get this. And now we're going to substitute into here. Again, the radius would be half the diameter. So over here, I'm going to carry this up here. The radius is going to be 0.007 meters divided by 2. And the length is going to be our 0.02 meters, like this. And then 2 times our length, 0.02 meters, plus our radius, which is 0.007 meters, like this. and put that all in your calculator. Notice that this is going to be a meters squared in the numerator, meters in the denominator, so we're going to end up with a meters. And we put in your calculator, it is 0.0014892 meters. Now we want to calculate the bio number, and remember what that is. That we did a little while ago. It's going to be the heat transfer coefficient times the characteristic length divided by the thermal conductivity. And if you substitute all the values, this was 30 watts per meter squared degrees C. Now one thing you'll notice a lot of times these heat transfer coefficients will be given like in meters squared C or meters squared K. Because we're dealing with differences in the temperature, you'll have the same value usually for if this is K or C, so you can interchange those. So actually the way it was given the problem, we were actually given a K here for Kelvin. And again, the characteristic length we just calculated. Like this. And then K was 97 watts per meter Kelvin, like this. And next we'll put this into our calculator. And when I did that, I got 4.606 times 10 to the minus fourth. And actually all the values cancel. So here we have watts cancel, meter, one of the meters canceled here, the other one canceled here, Kelvin canceled there. And this should be a dimensionless number, so just always check this to be sure that everything cancels properly. And notice what we have here. We have a number much less than 0.1. And so if your bio number is much less than 0.1, that means that this problem is a candidate, a good application for a lumped system. So we're going to go ahead and apply the equations now. Again, because the bio number was less than 0.1, much less than 0.1, we can use the lumped parameter approximation. We can use this equation that says that temperature T after small t seconds is going to be equal to the initial temperature of the object minus the fluid temperature. In this case, this is going to be air times the exponential E raised to the negative h. Again, h is the heat transfer coefficient. T is the time, however long you want to find the temperature for. Rho is the density of the material. Cp is the specific heat at constant pressure. And L is characteristic length, which we calculated a minute ago. And plus the fluid temperature. So we can substitute these values into the equation. So T is going to be T initial. Remember, given the problem as 5 degrees Celsius minus 35 degrees Celsius was the fluid temperature. Again, that's air in this case. Remember, when we're dealing with differences, we can use Kelvin or Celsius, or if we're with English units, it can be Fahrenheit or Rankine. Again, then times EXP CP. And we're going to go through and be sure to check all of our units. So we're going to have negative 30 watts meters squared degrees C. The time we were interested in what the temperature is going to be after 50 seconds. And if you look up in the back of your book, in my book it's table A2, the density of chromium is 7160 kilograms per meter cubed. CP is 434 joules per kilogram K. And the characteristic length, which we calculated a little while ago, was 0.001489. And that was in meters, like this. Now we want to check, and then that's going to be all plus our fluid temperature, which was 35 degrees C. Now, because we're taking the exponential here, these values should all come out to be dimensionless. So let's just check our units here. We have a meters cubed here and a meter here, so that's going to cancel one of these, so this is going to be down to a meter squared. That's going to cancel with this meter squared. Then, let's see, we have degrees K over here, but remember, we can use this C, again, we're dealing with differences, so this could be considered C. And actually, when I did originally, I guess I did actually state the problem with a K here. So actually the original problem had a K here. So we should change that to K anyway. So the problem statement had K here, and so I'll fix that, and the K's will cancel. And the kilograms are going to cancel. Now the only thing that's not going to cancel, we have watts here, and then we have seconds and joules. But of course, remember that a watt is a joule per second. And so the seconds will cancel here, and then the joules will cancel here like this. Now when I put this into my calculator, multiply by this difference, which is going to be negative 30, added it to 35, I got the temperature after 50 seconds to be 13.3 degrees Celsius, like this.